In this video, I will give a short presentation on our paper titled The Role of Feature Interactions in Graph-based Tabular Deep Learning. This work has been accepted at TMLR in March 2026. To set the stage, we are in a supervised prediction setting for a single tabular dataset, as depicted in the table on the left. Given features x1 and x2, we are trying to predict the target y. Each column could represent something else, such as continuous, categorical, or binary feature. Furthermore, we are viewing the table as a graph. We do not see it as a sample graph, where the nodes in the graph represent rows in the table. Instead, we see it as a feature graph, where nodes in the graph represent the features or columns in the table. The edges of a feature graph represent the relations between the features. What tabular data characterizes is that these feature interactions are heterogeneous. Each relation between each feature could be very different. This is in contrast with, for example, vision, where each feature represents a pixel. We are going to discuss two types of graph-based tabular deep learning methods, or GDTL in short. The first type of methods are graph neural networks, GNNs, and the second type of methods are attention-based methods. Let's first discuss GNNs, or graph neural networks, such as 2G-Former, INCI, and PhiGNN. So in this example, we are trying to predict year, given the features length, price, and age. So how does this look like? Typically, the first three features are being passed through a feature tokenizer, which elevates the cell values into embeddings, and these embeddings are being processed through a series of GNN layers. And finally, the target node is passed through a decoder to predict the target variable. So once this model has been trained to do prediction, we can extract the adjacency matrix out of the methods. And what these methods often claim in their papers is that they can do interpretability. So for this example, they could say something like, it makes sense that age and length have a strong relation because of some data-specific reason. What does it actually make sense? We need a quantitative measure for that. Now let us discuss attention-based methods, such as FT-transformer, Saint, and TAP-transformer. These work similarly as GNNs, but instead of a GNN, they have multi-head self-attention. And the object of interest for us is the attention map, which you obtain when you multiply the query and key with each other. Because you could also do interpretability with this attention map. This has been done in language, for example, with Birdfish, where you visualize how words attend to each other. You could also do this in a tabular setting, because if you average the attention map over all the test samples, heads, and layers, you obtain something that should represent something like the adjacency matrix. So the problem with these existing methods is that they cannot evaluate the feature interactions, i.e. the graph structure, as there is no ground truth graph in real-world data. A simple solution for this is to use synthetic data with a clear underlying graph. We use two types of data generation methods. The first one is based on multivariate normal, where the underlying graph is sampled from a Bernoulli distribution. And the second one is using a structural causal model, where the graph structure is coming from a DAG, similar as being done in tabular foundation models. For both type of data generation methods, we on purpose use relatively simple graphs with relatively simple feature interactions. Now, given this synthetic data, we're going to train them to do supervised prediction, as discussed before. Once training has been done, we're going to extract the learned graph structure and are going to evaluate it. We're going to do this with the ROC AUC. So we're going to compare the true binary adjacency matrix against the predicted weighted adjacency matrix. Here you see the results with on the y-axis the ROC AUC, on the top row multivariate normals, and on the bottom row for structural causal models. We do this for 1 attention-based methods and for 3 different GNN-based methods. On the x-axis, we vary the number of training samples. Both the multivariate normals and structural causal models are averaged over 3 different datasets and 10 seeds. You can see that in basically all of the cases, the ROC AUC is around 0.5, which is the same as random chance. This indicates that the learned graph structure of these GDTL methods does not represent any meaningful feature interactions. So why should we even care about the correct graph structure? Well, first of all, it improves interpretability. Second of all, it improves prediction. So how does this improve prediction? In order to show this, we're going to compare the default setting, that with a fully connected graph, to a graph pruned to the true edges only. So for a GNN, we will just remove those edges, while for attention-based methods, we would mask the attention map at those edges. So here you see a similar graph, but now on the y-axis, we've got the normalized R-square score. In green, you see the default setting, that of a fully connected graph. In red, you see the case where we prune the graph to the true edges only. You can see that in basically most of the cases, you get better performance when you mask the graph to the true edges only. So from this, you can take away that we should care about the correct graph structure inside these GDTL methods. So, to summarize, existing GDTL methods do not model the feature interactions correctly, because the ROC AUC is around 0.5. Furthermore, it improves prediction when the true graph structure is enforced. So there are several ways how we can improve this work. One of them is to use more real-like data. However, we have shown that even for simple graphs with simple feature interactions, the models cannot learn the correct graph structure. So an interesting next step is to improve the training procedure so that the correct graph structure is learned, both in these traditional deep learning methods, but also in tabular foundation models.